Welcome to You Got Hope Chemistry. I'm Hope, and you're about to learn some chemistry. So in today's lesson, we're going to take what we learned in lesson 1 and we're going to apply it to questions where we can actually make a calculation for K. So as a quick review, in the previous lesson, we talked about what equilibrium was, how do you know you're at equilibrium, and also how to write an equilibrium expression. Now, quite often the purpose of writing an equilibrium expression is to make a calculation. Now, this lesson is titled Simple Calculations of K because there's two kind of calculations that we're going to do in this unit. One's where we simply apply values of concentrations at equilibrium into an expression. So those are simple ones. Those are the ones we're doing today. And then we're also going to do ice table problems, which would give us concentrations either at the beginning before you reach equilibrium, or partially through, or at the end and at the beginning, and we have to figure out K values or concentrations. Those are much more difficult and will require their own lesson as well. So again, what we're doing is questions at equilibrium, not before equilibrium, but at equilibrium. All right, let's look at this first question here. It says, write the equilibrium expression for the following reaction. So the first thing I would do for an equilibrium expression is I would check the states to make sure this was a homogeneous mixture and cross out anything that doesn't belong. This is homogeneous because everything is a gas. The next thing I'd do is I'd probably highlight the coefficients as well because I have to raise these concentrations to their coefficient power. And then I make sure that I do products over reactants. So this would be the concentration of CO2 raised to the power of 1, but I'm not going to put that in, times the concentration of hydrogen raised to its coefficient, which is 4. This is divided by the concentration of the reactants raised to their powers. So I've got CH4 raised to the power of 1, and then I have H2O raised to the power of 2. So this is an equilibrium expression, and it's simply the ratio of products over reactants based on concentration. Now, we did this in the previous lesson. What we're going to do now is actually make a calculation. So in the second part here, it says, calculate the value of Kc given the following equilibrium concentrations. So the system is at equilibrium. So I can simply apply these values straight into the expression and plug them into my calculator. Now, these usually aren't very difficult. The biggest problems actually come from entering numbers into the calculator, making a silly mistake, something like that. Okay, so let's start with CO2 is 1.5 times 10 to the negative 2 raised to the power of 1. I have H2 at 6.50 times 10 to the negative 2 raised to the power of 4. I'm going to double bracket this so I make sure the numerator is calculated first and my calculator follows BEDMAS. I then have CH4, 1.0 times 10 to the negative 2 raised to the power of 1. And then I have H2O, which is 2.0 times 10 to the negative 2. And this is raised to the power of 2. I close that off. What to do now is pause the video and make the calculation on your own in your calculator. Okay, now that you've had a chance to plug it in your calculator, let's see if you got the same value as me. So plugging this in, I got 0.066939. Now this is a unitless value. It's simply a ratio. If you were to plug the units in, they wouldn't cancel out properly. You would get a weird value, and every time you calculated K, you'd probably get a different unit. It is unitless. It is a ratio over products over reactants. Now, I should convert this into scientific notation, and generally K values are written as 2 significant digits in a scientific notation format. So for instance, I'd move my decimal place back 2 spots. This would be 6 point. The 9 would round up the 6 to 7 times 10 to the negative 2. Again, 2 back. and there's my K value. So that's great. We have a K value, but what does it mean? Why do I even care? So again, review from our first lesson. K's tell us how much a reaction favors the products or reactants when at equilibrium. Now, the value of K is 6.7 times 10 to the negative 2, which is less than 1, which means that the position of the equilibrium or the favored side would be the reactant side. So we would say the reactants are favored anytime we have a K value less than 1. Now, in terms of writing a greater than or less than 50% sign above the arrow, I want it pointing towards the reactants because it's less than 50% forward. And then what would I have a greater concentration of? Well, again, to put it into perspective, this is the concentration of the products over the concentration of the reactants. And in order to get a value less than 1, your denominator has to be bigger, which means the concentration of reactants has to be bigger. So I have a greater concentration of reactants. So we're going to do another question. This one's going to require us to do a couple more steps, but the basic goal is going to be the same. We're going to want to be able to calculate a K value and then talk about what that K value represents in the end. So this one's talking about chlorine gas and hydrogen gas reacting, and it says at a certain temperature. K values are affected by temperature, and so a K value for the formation of hydrogen chloride gas at one temperature would be different than a K value for hydrogen chloride gas at a different temperature. So you have to be very careful that you don't try to memorize anything like, oh, I know this reaction has a K value of this. Every reaction has a different K value for every different temperature. So this one just says at a certain temperature. I don't know what it is. Something I noticed that's drastically different is they've given me the volume of a container. Now, because these reaction calculations are based on concentration, I'm going to have to calculate the concentration of chlorine and hydrogen gas as well as hydrogen chloride gas because they've only given me the number of moles. So this one says the equilibrium mixture, so I am at equilibrium, was found to contain 0.55 moles of chlorine gas, 0.65 moles of hydrogen gas, and 2.4 moles of hydrogen chloride gas. Again, all of these questions are at equilibrium. So the first thing we need to do is calculate 3 different concentrations. We've got to calculate it for chlorine gas. We got to do a calculation for hydrogen gas, and we got to do a calculation for hydrogen chloride gas. Now remember, from Chemistry 20, concentration is equal to the number of moles divided by the volume. This is moles in the unit of the mole, and this is volume in liters. So if it's in milliliters, you would have to convert it to liters, and same thing with moles. You have to have everything in the same unit of moles, so it could be all millimoles or all moles or all kilomoles. As long as the unit of the mole is consistent, you're fine. So I'd like you to pause the video now and try calculating those 3 concentrations using a 3-liter volume and then those numbers of moles for each substance. Okay, now that you've had a chance to do that, we're gonna do the 3 calculations and you'll check your work. So C is equal to N over V. So for chlorine gas, it was 0.55 divided by 3 liters. So the concentration here would come out to 0.183 repeating moles per liter. Okay. Hydrogen would be 0.65 moles divided by 3 liters. So if you punch that in, it would come out to 0.216 repeating moles per liter. And for hydrogen chloride, this is 2.4 moles divided by 3 liters, and this would come out to 0.80 moles per liter. Now, I would not round these values at this point. I would keep all of these digits in there because we only round when we get to the end of the question. Okay, the next thing I'd like you to do is write the balanced chemical reaction for chlorine gas reacting with hydrogen gas to form hydrogen chloride gas. Pause the video now and give it a try. Okay, now that you've had a chance to do that, I'm going to write out the reaction. So it's going to be H2 gas plus Cl2 gas in equilibrium. I must have an equilibrium arrow. And then hydrogen chloride gas is HCl gas. I need to have 2 moles of that, so I know I'm going to have the concentration raised to the power of 2 in my equilibrium expression. So there's our balanced chemical reaction. The next thing I'd like you to do is, using that balanced chemical reaction, write out the equilibrium expression. Pause the video now. Now that you've had a chance to do that, let's give it a try. So K is equal to products over reactants concentration, so square brackets for concentration, HCl raised to the power of 2 all over H2 raised to the power of 1, Cl2 raised to the power of 1. I double check, are all my states the same? Is this a homogeneous mixture? Yes, it is. I double check, are the states, are the coefficients correct? This is a 1, yes. This is a 1, yes. This is a 2. I got my 2 there. Perfect. Okay, the next thing I'd like you to do is take your concentrations from part A, substitute them into the equilibrium expression, and calculate the value of Kc in part D. Pause the video now and give it a try. So now that you've had an opportunity to give it a try, let's do the answer. Substituting my values in, I have 0.8 squared on top. I have 0.183 repeating on the bottom times 0.216 repeating, and I'm going to double bracket that just to make sure it's okay. And then I'm going to plug this into my calculator and get an answer. And I got a value of 16.1119. I will convert this into scientific notation, so this would move over 1, and this would be 1.6 times 10 to the power of 1. So K is greater than 1. And at this time, what I would like you to do is take all this information and use it to help fill in this chart. Pause the video now and try filling in the chart. Okay, now that you've had a chance to do that, let's fill it in. So I could either put in 16, or I could put in the 1.6 times 10 to the 1. Remember, this is unitless. It's just a ratio, and the ratio essentially is 16 to 1. All right, which position of the equilibrium is favored? Anything greater than 1 favors the products. And all that means is you have more products than you have reactants at equilibrium. The next thing I'm going to do is I'm going to write my reaction in here. So H2 gas plus Cl2 gas makes HCl gas. And I have to put in the greater than or less than 50% sign above the arrow. Now, because this favors the products, it's greater than 50%. And so I have to have the greater than sign pointing towards the products, so greater than 50%. And then, of course, what do we have a greater concentration of? Well, we have a greater concentration of products because, again, if my ratio is 16, it's really 16 over 1. This is the concentration of the products in comparison to the concentration of the reactants. So I have more products than reactants when the system is at equilibrium. The last question we're going to do is got a little bit of a twist to it compared to the questions we've already done. In this case, we have actually been given a K value, and the question is actually asking us to calculate a concentration at equilibrium. So all this will require is for us to rearrange the K expression and solve for a concentration rather than solving for K. So what I'd like you to do is write out the equilibrium expression for this reaction. Pause the video now. Now that you've had a chance to do it, let's check our answer. So K is equal to products over reactants, so it's the concentration of NO2 raised to its coefficient 2, all over the concentration of the reactant, which is N2O4 raised to the power of 1. Again, I'm going to double check. Is this a homogeneous mixture? Yes, it is. They're both gases. Have I incorporated the coefficients into the expression? Yes, I have. The most common mistakes here are really silly ones where somebody forgets to enter something in. All right. The next thing we need to do is we need to isolate N2O4. So we have to do a bit of algebra to move it to the other side and isolate it. I'd like you to pause the video now and try to do the rearranging on your own. Okay, now that you've had a chance to do that, let's move it up to the other side by opposite operation, which of course will be multiplication. Because it's being divided, I have to multiply it up to the other side, so N2O4. On this side, it would be N2O4. That's going to cancel this out. But now my issue is I need to get K to the other side. Because K is being multiplied, the opposite operation is division. I'm going to divide this by K. I'm going to divide this side by K. And that's going to cancel out my K values. This will leave me with the concentration of N2O4 is equal to the concentration of NO2 raised to the power of 2, all divided by K. So now what I'd like you to do is I would like you to enter in the values and solve for the concentration of N2O4. Pause the video now and give that a try. Now that you've had an opportunity to do that, let's have a look. So the concentration of NO2 at equilibrium is 1.5, and this is going to be squared. The K value is 0.09. Now we just got to punch it in our calculator and get an answer. So the value I got was 25. And of course, this is moles per liter. This is not unitless. This is a concentration. Our K value, which is 0.09, that is unitless. But I'm calculating for a concentration, which is here. This does have a unit. It is in moles per liter. So the last thing I'd like you to do is use our K value, which is 0.09. So our K is less than 1. And I would like you to take that and use it to solve the rest of this box. Pause the video now and give it a try. All right, now that you've had a chance to do it, let's fill it in. I'm going to write this as 0.09, or what would probably be better is 9.0 times 10 to the 1 to negative 2. Because K is less than 1, this system favors the reactants. Now, if I was to write a greater than or less than 50% sign, it has to be pointing towards the reactants, which is essentially saying this is less than 50% forward. And then, of course, we have a greater amount of reactants. So this is simple calculations of K and also interpreting those K values and what they represent. I hope you have enjoyed this lesson of You Got Hope Chemistry. See you next time.